stop me. This is very informal. If y'all have other questions too on the homework, whatever, have those ready to go. And we'll just work through stuff. And then if y'all think of questions, just, you know, shout them out. So this one actually was kind of derived from the homework, but there's an extra twist to it at the end. So this one, you may recognize this. There's a problem on your homework, and it says, as we exercise, our bodies metabolize glucose with oxygen, converting it to CO2 and water to supply the energy necessary for physical activity. Now, you didn't have to write the balanced equation for this, I think, or maybe you did. We're going to write it here, and then we're going to start doing some conversion stuff, okay, between kcals, because we have the delta H for this. This will just ask us what's the sign for delta H. And then the next part is about a jogger. There's a problem about a jogger on your homework. So let's write the balanced equation for this. This is essentially a combustion reaction. Well, not really, kind of. You have glucose, C6H12O6, and oxygen. Okay, so we write that out. Those are our reactants, C6H12O6 with oxygen. Okay, and oxygen is diatomic, right? And then it tells you your products are CO2 and water. So let's just draw our arrow. We got CO2 and water. Now we need to balance it. So we have 6 carbons on the reactant side in glucose. So we need 6 on the product side. So I'm just going to put 6 in front of CO2. And then we got 12 hydrogens. So I need 12 over here. So I'm also going to put a 6 in front of water. And then 6 times 2 is 12 oxygens there, plus 6 more is 18. And I already have 6 over here in this. So if I'm trying to get 18 total on this side and I already have 6, I just want 12 more out of this molecule. So I'm going to put a 6 right there. So your coefficients to be 1, 6, 6, 6. Okay, each mole of glucose produces 678 kcal of energy. Key word here is produces, right? Each mole of glucose produces. So each mole that's metabolized in our body produces that much energy. What's the sign for delta H? What do y'all think? Essentially, it's just saying, is it positive or negative? It's negative, okay? If a reaction produces heat or produces energy, that's exothermic, so this would be a negative. That's it for this question, okay? All right, let's go to the next slide. Okay, this is the one that you probably recognize this part from your homework. And then number 4 is something I added. Sorry, these slides are a little bit weird because they're larger than the actual screen size. Okay, an individual jogging at 5 miles per hour for 30 minutes would burn 272 kcal. How many of y'all remember a problem like that on your homework? What did you need to do here? It says how many moles of glucose would need to be metabolized to generate this amount of energy in the body? What do you got to do? It gives you a certain amount of kcal. This is now all the stuff about the jogger, you don't really need it here. You're focusing on, it says, would burn 272 kcals. If you run for that long, do that much physical activity, you're going to burn that many kilocalories. So how many moles of glucose would need to be metabolized in the body to generate that amount of energy so you have the energy to go run? Well, what do we need to do? Do what? Convert kcals to moles of glucose. How do we do that? Okay, we're going to start with 272 kcals. We're trying to figure out what's the equivalent moles for this amount of energy. So this is our starting point. Now, what do we do? One mole? It's not this over 1 mole because this is just kind of the number the problem gives us. We don't actually have a relationship for this number. But we should have a relationship for something to units of kcal so that we can cancel kcal and convert to moles. Otherwise, we can't do this problem. Do we have kcal glucose? We need something from this problem up here. Actually, we need information from this page right here. We need to derive a relationship between kcals and moles of glucose. Because it says right here, each mole of glucose, how many is each? 1. 1 mole of glucose produces that much energy. So if I metabolize 1 mole of this, I'm going to produce this number of kcals on this side. Now y'all got it. So the relationship is 678 kcal. You can write it out like this, or you can plug it straight into the problem, is equivalent to 1 mole of glucose, okay? So if you get to a problem, I mean, sometimes I'll do problems where there's 2 or 3 parts. And if you get to part 2 or 3 and you don't know what to do, go back and reread the initial parts. Sometimes, oftentimes, there's information in those parts you need for those later parts, okay? Exactly like here. So we want kcals to cancel. So it's for every 678 moles of kcals of energy is related to 1 mole of glucose. I'm just going to put a G for glucose. So if we metabolize 1 mole of glucose, we'll produce this much energy, but we only need this much energy. So we're just gonna relate that to the number of moles of glucose. It's probably gonna be less than a mole, right? So you do 272 divided by 678. 0. What? Okay. So right under half a mole of glucose would give that amount of energy in the body. Okay. So this is just a 1-step conversion problem. I think the challenging portion of this is looking at the problem and then pulling out the information that's asked you. It's all right there for you. You just have to realize what it's asking you and then what you need to do. And that is where the hard part comes in, converting and figuring out what units you need and what the relationship is, okay? All right, and then I added this little twist on the bottom. How many of you like energy bars? Eat energy bars? An energy bar contains 20 grams of glucose. How many energy bars would need to be consumed to generate the same amount of energy in question 3? I like energy bars, but they're so high in added sugar sometimes. I try to find ones with natural sources of sugar, but an energy bar is 20 grams of glucose. Okay, let's reread this. How many energy bars would need to be consumed to generate the same amount of energy in question 3? Right up here. Okay, thoughts on this? What do we need to do? Huh? The molar mass of glucose. Okay, you could easily calculate that, but to save time, it's around 180.156. What are the units on this? Grams of glucose per 1 mole of glucose, right? Grams per mole. What can we do with that? What we solved for up here was moles of glucose. We have another relationship in problem 4 we need to go ahead and write out. It'll probably help us see. 1 energy bar yeah, 180.156 contains 20 grams of glucose, okay? That's another relationship that the problem gives us here. Again, you've got to be able to read these and pull that information out. So how many energy bars? Okay, so we know if we're still talking about, it says the same amount of energy in question 3, which is this amount of energy, okay? The 272 kcal. If we need to produce this amount, we don't get glucose in our body unless we eat food that gives us glucose, okay? So how many energy bars would we need to eat to generate this amount of energy in the body? Well, we know that much energy is already related to 0.4 moles of glucose. So what can we do here? Do what? Start with the 0.4 moles, okay? We've already done a step of this problem up here in part 3. We've already related that to that. So start with this. 20 grams of glucose? Because the only thing we can do with 20 grams of glucose is okay, there's probably 2 ways you could work this problem. You could take 20 grams of glucose and see how many moles of glucose that is using this number, the molar mass, but then you still have to use the 0.4 moles because this is related to that amount of energy. There's 2 ways you can work this problem. You could start with 20 grams of glucose, convert 20 grams of glucose to moles and write a new relationship, or you can start here and do what we're about to do. Okay, now what? I want to cancel moles of glucose. What can I convert to? With the molar mass, I can convert to grams. So it says for every 1 mole of glucose, it's 180.156 grams. And then we can cancel, so moles cancel right there and right there. Now we can plug in this relationship and we can cancel grams and convert to a number of energy bars. Okay, does that make sense? So for every 20 grams of glucose, it's 1 energy bar. And then grams cancel. And then now we can just calculate how many bars. So 0.4 times 180.156 divided by 20. How many energy bars would that be? 3.6. But who's going to stop at 0.6 bars? Who's going to eat 4 energy bars in a row, though? Not me. Okay. But anyways, that's how you work that problem. So again, I like this problem because you got to be comfortable with plugging in molar mass, which is a concept you guys know very well. It's just applied here in a kind of a new context. And then the relationship between kcals and moles using a chemical reaction.
So if we started with the 20 grams, and we get that.
If you started with the 20 grams, what you would need to do is say, okay, 20 grams of glucose, and you need to convert that to moles, okay? It's 180.156 grams for every 1 mole, okay? And then you get a certain number of moles, okay? And then you say this amount of moles is still equal to 1 energy bar. 1 energy bar is gonna give you that many moles of glucose. Then you would still need to take this 0.4 moles right here and then cancel moles and convert to energy bars. So either way, you're using all the same numbers. Okay, any questions on this problem? I think it's a great problem. What was the most challenging part of that? Yeah, I agree. So again, what helps you though, I think, is writing out the information you know that the problem tells you, any relationships on the side, and then look at what units you need to cancel and where you're trying to go. And that should help. Okay, this one is very similar to several problems you had on the homework. And then we did a practice problem like this in lecture, and I just want to kind of reinforce a few of the same ideas before we move on. It's another combustion reaction with methane, and you're given the associated delta H. And this one says how much heat in kcals is released or absorbed with 0.77 moles of CH4. So here we're kind of working backwards with what we did with the energy bar problem. So what do I need to do here? Multiply what the delta H is. Okay, 0.77 moles of methane, CH4. Okay, why are you saying over 1 mole? Yes, but you have to take into account for CH4 what the coefficient is. If we burn or combust 1 mole of this, then we're going to get that much, that many kcals. But if the coefficient was like 2, if this was asking for oxygen instead of methane, if it said like half a mole or 0.77 moles of oxygen, then you would have to put a 2 down here because you got to always take into account what the coefficient is. You can't just write over 1 mole all the time, okay? Even though the units of this are per mole, okay? You have to take into account what the mole ratio is for that particular reactant or product. So it is 1 mole here. And you just do the absolute value of your kcal, of your delta H. So if we burn 1 mole of that, we'll get 213 kcal. But if we only burn like 3/4 of a mole, we should only get 3/4 of the amount of energy, right? So what is 0.77 times 213? Negative. Well, we can just write the absolute value again. So what'd you say? 64. You don't here. It's just asking for a quantity of energy, okay? So when you're just asking specifically for a quantity, it doesn't make sense to say a negative quantity, okay? Here, the negative tells us this is an exothermic reaction. The negative is communicating something there. When you're doing the problems, you can just plug in the absolute value.
If you were doing it like the 202, would you just put it over?
The 202, what do you mean? Oh, sorry, the 2 moles of oxygen, yeah.
So would you just put it over 2, like 213 over 2, or would you multiply the 213 by 2?
You would just put 213 and on the bottom 2 moles of oxygen. Mm-hmm. You just plug in that coefficient. Yeah. Okay. Now we're talking about oxygen. How much heat in kcals is released or absorbed? Oh, it keeps saying released or absorbed. We know this is released, right? Because that's negative. So in both cases, it's released because it's exothermic. With 55 grams of oxygen. So this is an added step. What do we need to do here? Molar mass. So we're going to start with the 55 grams of oxygen. Here's what we need to do. We need to go grams to moles of O2. And then we need to go moles of O2 to kcal of energy. Okay. So 55 grams of O2. What's the molar mass of oxygen? Not 16. 16 times 2, because 1 mole of oxygen has 2 oxygen atoms per molecule. So you got to take into account two of those oxygen atoms. So it'd be 32 grams of oxygen for every 1 mole of oxygen. So grams will cancel out. Now we're just going to go from moles of oxygen to kcal. So exactly what we said in the hypothetical scenario I was saying earlier. Here, our coefficient now for oxygen is 2. So for every 2 moles of oxygen consumed in this combustion reaction, we're producing 213 kcal. Okay, so you always just go look at your balanced reaction, look at the coefficient for that particular compound or molecule, and you write that so that moles cancel, and then you write the absolute value of your energy related to that. So now we'll do the 55 divided by 32 times 213, divide that by 2 in the end. What do we get? 183? The 164? This is just for, that's a completely separate problem. So we're just starting with a new problem, and we have a new substance, okay? Yeah, don't always assume problems are tied together, okay? If I say, consider something in the previous problem, or the same energy value from part 3, okay, like it did in the other one, then, you know, you got to go back up and look at what the previous problem said and how much, you know, I'll try to give a hint if the problems are associated together. Sounds like your answer from part 2, you know, blah, blah, blah. Okay. All right. Any other questions on this one? So feel comfortable converting between moles and kcals and moles, all the way to grams if you have to. Okay. All right, here's the delta S problem. Predict the sign of delta S, positive or negative, for the following reactions. So if you're looking at number 1, we have magnesium. It's a metal, so it's a solid. With oxygen, it's a gas. Magnesium oxide, it's a solid. What do y'all think about this? Is delta S, is this order increasing or decreasing? Huh? It's decreasing, right? You got a gas and a solid on this side, 2 reactants, but you only have 1 product. Okay, you have gas, and over here you just have solid. So this is a negative delta S. This order is decreasing. You're becoming more ordered. Okay, and remember, what does S stand for? Entropy. Okay, so you'd say the change in entropy is negative. All that's the same vocabulary stuff here. Okay, what about this? Here's glucose, solid, breaks down into C2H5OH, which is a liquid, and CO2 gas. What do y'all think about that? Definitely positive, okay? You got 1 reactant, 2 products. You could look at it that way. You got 1 mole of stuff breaking down into 4 moles of stuff because you got a coefficient of 2 and 2 makes 4, or solid making liquid and gas. And we know these states of matter are way more disordered than a solid, okay? 3, you've got 2 NH3, that's a gas, ammonia gas, plus carbon dioxide gas makes liquid water. And then this molecule, NH2, CO, NH2, which is aqueous. What do y'all think about that? It is. Why is it decreasing?
I was thinking 2 on the outside, 2 gases.
And you got total 2 different gases, 3 moles of gas total. Liquid and aqueous, these are substances that are more ordered than gases, okay? Only 2 moles of stuff. So yeah, delta S is negative. Okay, good. Hopefully you feel comfortable doing that on the exam. Don't say that. That's not true. Which combination of delta H and delta S for a reaction is not spontaneous at low temperatures, but can become spontaneous at higher temperatures? Spontaneous at higher temperatures. What do y'all think? When I say combination, I mean like the positives and the negatives. Remember that table? We had the 4 different scenarios of the positive delta H, negative delta S, or both positive or both negative. We played around with numbers on this one. So there was a table. Let me see if I can find it. It's right here. Before equilibrium, so I was right. There we go. There we go. So we had this table and oh, you know what it did? It signed the computer host. Now I should be able to. Okay, I think we're back. There we go. So if we had a positive delta H and a positive delta S, we know what's the equation? What's the equation for delta G where we're considering how this all affects delta G? Yeah, you need to have this equation memorized if you don't. Delta G equals delta H minus T times delta S. So if we're considering this scenario, if this is a positive number right here, and this, we know temperature will always be positive because I said you can't have any sort of thing as a negative Kelvin. The Kelvin scale stops at 0. No such thing as a negative Kelvin. So this will always be positive, okay? And if this number is also positive, I like to put this whole thing in brackets. This negative out front makes this whole term negative. So as long as this number is bigger than that term, you get a positive delta G, which is positive delta G is spontaneous or no? What does a positive delta G mean? Endergonic, right? Endergonic, which is not spontaneous, not favorable. Okay, but the higher you increase temperature, you raise your temperature bigger and bigger and bigger and bigger. Eventually, this negative number, this negative term, could be bigger than just your delta H. And then when that happens, your delta G can become negative overall. So this is where we played around with numbers. We said, for example, if you have a positive 10, I'm just throwing in random numbers, and said minus a temperature is like 1 times, let's say delta S is 2. 10 minus 1 times 2 is 2. So 10 minus 2 would give you a positive 8, right? So if we keep delta H and delta S the same, but we really crank up temperature to 20, from 1 to 20, now we have a really high temperature. Now 10 minus, what is that, 40 is going to give you a negative 30. So then you could, at high enough temperatures, get a negative delta G. These are just hypotheticals, whole numbers we threw in. But it's this, this combination of delta H and delta S, okay? A positive and a positive, that the delta G can go from positive to negative depending on what temperature it is, okay? Questions on that? Why that works, how that is? I feel like that doesn't sink in super well.
So we memorize the table too.
But you definitely need to know the information on the table. Okay. Oh,
So the penalty question?
Huh? Did we answer the question? Yeah. Which combination? This combination. Positive and positive. You have a question you want to ask?
No, I thought I was asking based off of the problems we just looked at, so I was confused.
Huh?
Never mind, I'm good.
You sure?
I was confusing myself.
Okay. All right. This one's a totally separate problem. The process of boiling a liquid has well, let's think about boiling a liquid. Any liquid. Any liquid. Okay. Let's just say water. Water's a liquid, right? So here's what I encourage you. Anytime I give you a problem like this, where it's kind of vague, just make up your own liquid, all right? Just think of the simplest one you can. So draw a chemical reaction for this. Boiling a liquid. So your reactant is what state of matter? Huh? Liquid. And your product is the same thing, because we're just changing states of matter here. And what state of matter is my product going to be? Gas. So let's look at this reaction. Okay. Positive enthalpy change, positive entropy change, positive enthalpy change, negative entropy change, negative enthalpy, but positive entropy, negative or negative. Not enough information is given. What do y'all think? So it's asking about the sign on delta H, which is your enthalpy. And it's asking about the sign on delta S, which is your entropy. So what would the sign on delta H be here? Is this exothermic or endothermic? If you're going to boil something, does that reaction, the actual reaction itself, give off heat? Or does it have to absorb heat? Yeah, it's got to, that water has to take heat in for these molecules to spread out far enough to be considered a gas. Okay? So does that mean this is positive or negative? Positive. And then what would you say for delta S here? Positive. Disorders is increasing. So that matches which one? A, right? Does that make sense? Does it help when you have something to look at though, right? It's really hard to imagine that all in your head. So if I give you something like that, you know, write it out and look at it and consider it that way. Do I? So I just was thinking of the process of boiling a liquid, okay? So I mean, you could write this. You could write substance A is a liquid, goes to substance, same substance A, but in a gas form.
No, I was talking about the H is like, I don't know which the H is.
Enthalpy and entropy. Okay, so enthalpy is the change in energy. If you're looking at the, you have to consider, is it going to need to break, are you breaking bonds or are you forming bonds? Remember, we said breaking bonds requires an investment of energy. Forming bonds releases energy. So here, I have water molecules. Sometimes it helps if I draw this out. So here's a water molecule. Here's another water molecule. The spheres are oxygens and the circles that are white are hydrogens. Here's another oxygen molecule. And we know water is held together with hydrogen bonds, okay? Connecting, I'm sorry, it's not bigger, so I don't think you can see very well. But all these water molecules are held together with these dotted lines representing intermolecular forces, right? You can have a whole web of them. And to break those apart into a gas where they're genuinely all spread out and they're not interacting at all because there's nothing holding them together. The breaking of these intermolecular forces requires an investment of energy. Okay, because breaking bonds requires energy. Forming bonds releases energy. So if something requires energy, that's an endothermic process. Endothermic meaning this plus heat. Okay, heat is considered a reactant. You got to heat that up to break it apart into this. Okay, does that make sense? Okay. Next one. Okay, so we had this reaction earlier, and we were given the delta H, so we calculated a few things. Now, if I give you the delta S, I say calculate the delta G for this reaction. Okay, it says for the following reaction, we were working with this earlier. I'm giving you a delta S, which is negative 88.5 joules per mole Kelvin. Calculate the delta G for this reaction. Here's your delta H. So if we're going to calculate delta G, which here's our equation for delta G, what do we need to do? I'll just write it on the iPad too. It's always more helpful in the recordings when I do that. Okay, what do we need to do? Because our equation is this, delta G equals delta H minus T delta S. Oh, you know what I didn't give you? The temperature. Okay, so I'd have to give you that. Let's say at 25 degrees Celsius. So what's the first thing we need to do? Convert to Kelvin, okay? So step number 1, say 25 degrees Celsius plus what? Yeah, you better have that memorized. 1.5. Okay, equals 298.15 Kelvin. And the 0.15, don't forget that. Okay, what's the second? So now we got our temperature here. Here it is. What's the second thing I need to do? So I need to take my delta S. The units do not match delta H, right? I need to make the units on delta S match the units on delta H. So this is going to be even more complicated than what we practiced in lecture. So I think delta S was what? Negative 88.5 joules per mole Kelvin. So let's take that number. We're going to start with that. Negative 88.5 joules, and write it as a fraction like this, moles times Kelvin on the bottom. And I want to convert joules to what? What am I trying to convert joules to? kcal. How do I do that? Huh? You gotta know this number. How do we convert? We can only go joules to calories or joules to kilojoules. Which one do you want to do first? Joules to calories. Okay. So joules to calories. How do I fill in the numbers? Flip that. 1 calorie is 4.184 joules. But you have the number right. Okay. Calorie is a bigger unit. All right, now let's keep going. I mean, you get your answer here. There's one more step. I want to go all the way to kcals, right? 1,000 calories equals 1 kcal. All right. Joules cancel, calories cancel. So if you do negative 88.5 divided by 4.184 divided by 1,000, what do we get? 0.02? 21? Okay, that's good. Kcal per mole. The per mole Kelvin don't go away. Did I get the number right? That's right. Don't let me forget the negative. There we go. Okay. Now we have, this is our delta S, right? We just solved for delta S. There's our delta S. Yeah.
So when do we use the absolute value and when do we not? So here we do use negative.
Yeah, whenever you're plugging in for a delta G, you always put in the negatives and the positives. Those absolutely matter because that'll affect your sign of delta G. But if I just give you a chemical reaction, I say, you know, if you're trying to draw a relationship between kcals and moles or something like that, like, and you're calculating a number of kcals from a number of moles or grams given, you just use the absolute value of the kcal then. Okay, not when you're solving for delta G though. When you're solving for delta G, include all the negatives and positives. Don't leave those out. Okay, so now what should I do? Delta G equals, plug in our delta H, which is 213, negative 213 kcal per mole. Don't forget the negative. And then it's delta H minus, I put this part in brackets or parentheses, our temperature, which is the 298.15 Kelvin, times, it's multiplied, times delta S. And we just saw for our new delta H, which is negative 0.021 kcal per mole times Kelvin. And you'll see the Kelvin cancels right there with the one in the delta S term. And we just end up with kcal per mole, and you can add and subtract those units since they're the same. We do the negative 213 minus the product of 298.15 and negative 0.021. So what do we get overall for our delta G? Anybody? I know some of y'all got it. Y'all just looking at me. Candace, what'd you get? I saw you punching it in.
Negative 206.
Is that right? Kcal per mole. Okay, there's no surprise here. You're going to have to solve for delta G on the exam. Do y'all ask me questions now? Any questions on what we did with delta S, what we did with temperature, how we plug things in? Any questions on this? The 25, I forgot to include that in the problem. Yeah. You have a question, Justin? Delta G? Yeah, in lecture, like when I first introduced this, I always gave you like calories on this. So all we did was calories to kcals. But this was just an extra step going from joules to calories and then to kcals. So all I'm telling you is on the exam, you will have to calculate for delta G. You have to solve for delta G. Okay. So make sure your temperature is Kelvin. Make sure your units on delta S match delta H. Okay. And everyone, let's make sure our masks are all the way up. I know it's not fun. Okay, write the equilibrium constant expression for the following reactions. What do we do here? The product over the reactants, right? So I'm saying write the expression for K, which is the concentration of products. If you have more than one product, it's product times product raised to the power of their coefficients, right? You plug those in as exponents. If you have anything besides a 1, over the concentration of reactants. If you have more than one reactant, it'll be reactant times reactant. And what do we not include? We don't include solids or liquids, only things that are aqueous or gases. So A here, shall we? Somebody tell me, K equals what? I don't have any numbers to plug in. I just want you to write the expression based on what chemical formulas you have. Okay, H2S, power of 2. It's exactly right. Okay. In the yellow, I don't know if you can see yellow very well. That's my product. So my product is on top. Coefficient, I'll highlight in blue. This is my coefficient. So there's my coefficient. And then the reactants we'll highlight in green. That's a reactant. That's a reactant. So you put those on bottom. To their coefficients, we only had one, which was the 2. Okay? Make sense? All right, B. Let's do another one. Somebody else tell me B. Okay, what is it? S times. Do what? Okay. You raising your hand? That's exactly right. We don't include solids. So this is not right. We just got to take this out. Okay, now what?
Solid and liquid, right?
Don't include solids, don't include liquids, but anything aqueous or gases, you do include. Mm-hmm. And those all have a coefficient of 1, so that's right. Are you getting the hang of it? All right. We'll do one more. We'll do C because the next part, next slide is about equation C. So we need to go ahead and write that one for the next question. So here, what's my equation? Okay. All right, D. We could write D, I'm sure. All coefficients of 1 there. You just don't include carbon because it's a solid. Okay. All right, now considering reaction C, which is this one from the problem above, solve for the equilibrium constant. So solve for K with the given equilibrium concentrations. So then I give you a value. I give you numbers, and M just stands for molarity. It's just the unit of concentration. But K, when you solve for K, is always unitless. So you really don't have to worry about units here. What can you say about equilibrium conditions for this reaction? So let's just solve for K first, and then we'll tackle that second question. So what do I need to do? Just plug those numbers in, right? So it should be K equals, keep the same formula. The concentration for the BRCL 0.55 is going to go right here. So it'll be 0.55 squared. And then the CL2 and BR2 are on the bottom, multiplied, coefficients of 1, so we don't raise those to the power of anything. 0.72 times 0.115. So in your calculator, if you're going to plug it all in at one time, put this whole thing, like put these numbers in parentheses. You don't have to put that in parentheses. You can just say 0.55 squared, but divided by these in parentheses. Because if not, your calculator probably won't give you the right answer. Anybody got the value of K? 0.65? 3.65? Sorry, missed that 3. 3.65. Okay. Now, so that's the first part. What can you say about the equilibrium conditions for this reaction? What can you say? What do I mean here? What am I asking you? Yeah, y'all remember this slide right here? I think it's a really important one. Oops. Whoops. Oh, I passed it. Right there. Y'all remember that slide? This is what I'm asking you. I'm asking you to comment based on the size of K what your equilibrium conditions are. You got more products, more reactants, the forward or the reverse reactions favored? Huh? I mean, to answer this kind of question, you need to know that information, right? So what would you say about this? More products, you could say the concentration of P, or you could write products, is greater than your concentration of reactants at equilibrium. You could tell me several things. You could say the forward reaction is favored. Whoops, FAB. I'm not spelling this right. FAB. Okay. You could say I'm going to have more products than reactants at equilibrium. Several ways you could communicate that, okay? Any questions on this? Okay. I think, is this the last problem I had planned? Yeah, this is the last one I had planned, and then I'll take as many questions as y'all have. Do what? Hydrogen chloride can be made from the reaction of chlorine and hydrogen. For this reaction, K equals 26 times 10 to the power of positive 33. And delta H equals negative 44 kcal per mole or negative 184 kilojoules per mole at 25 degrees Celsius. Okay, so a few initial questions here about K and delta H, and then it gets into Le Chatelier's principle. So is reaction endothermic or exothermic? No math required here. How do you know? Negative delta H, so exothermic. Reactants or products are favored at equilibrium? Products, how do you know? K is much, much, much bigger than 1, right? You can look at your arrow diagram, that color-coded one I just showed you guys, and confirm with yourself that products are highly favored at equilibrium, okay? Explain the effect on the equilibrium of doing the following things. Increasing the pressure by decreasing the volume. Same thing there. Increasing pressure, decreasing volume. Okay, so basically we're just going to say if the equilibrium is going to shift left or right or no change. What do y'all think about this one? Increasing pressure. Well, what do I need to do?
We're increasing pressure on the reactant side.
We're just increasing pressure on the whole system. What did you say? Look at the moles of what? Yeah, specifically the moles of gas, which everything is gas here. But if you have a reaction where not everything's gas, you're just considering how many moles of gas you have on each side. So how many moles of gas do I have on my reactant side? 2 moles of gas. How many on the product side? Whoa, so what's going to happen here? It won't want to shift one way or the other. So you'd say no change on this one. So this is unique that you have the same amount of moles of gas on both sides. But you would just say no change. Okay. Now, if it was different numbers, like if this was 1 mole of gas, what would you say? Which way would it shift? It would shift towards the reactants or towards the left. Okay. When you increase pressure, it shifts to the side with fewer moles of gas. But if the amount of gas is the same on both sides, then it's not going to want to shift one way or the other. Does that make sense? Okay. Increasing the concentration of HCl. Which way will it shift then? Yeah, to the left. When you increase the concentration of a product, this is your product. When you increase that, it's going to shift the other way to use up the excess that we added. Okay, which there is towards the reactants. Okay, decreasing the concentration of Cl2. I'm just listening. I'm letting y'all work it out.
I thought once you remove it, it's going to go to where something is removed. To balance.
Decreasing and increasing are opposite things. When you increase something, it shifts to the opposite side. When you decrease something, it shifts towards that side. So if we're taking this away, like we're taking this and we're decreasing it, taking it out, it's going to shift to replace that, which means it will here shift left. Questions on that? Because none of you said right. It's okay if you're confused or got the wrong answer. Now's definitely the time to get it wrong and ask. Yes. So if we are taking, see, I put a downward arrow because that means I'm like decreasing the concentration of CO2. That means we're like taking it away, okay? If we're taking this away, then we have deviated from original equilibrium concentrations. We're lower on this side, okay? So the only way this reaction within itself can produce more of this is by taking that. I mean, this should be a reversible reaction. Taking that and breaking it down into more of that and more of that to restore some of what we took away, okay? So if we're running the reaction this way, equilibrium is shifting left. That's the left direction. You're considering which way is the reaction going to run, left or right. The reverse reaction is going to run or the forward to either replace or use up what we add, okay, or take away. Does that help some more? Okay, now increasing the concentration of H2. It'll shift to the right. Okay, again, if what I'm saying isn't making sense, let me try that balance analogy. In this case, we're increasing the concentration of this, so I'll put a little upward arrow there. So it's like we're adding weights. If these are both weights, it's like we added another weight on this side. So the balance is going to be weighed down. It's going to tip down on that side, okay? So to get the balance even again, it's going to react that plus some of the excess H2 we added and make more HCl to add weight to this side to get it even again. So it's going to run the forward reaction. Shift, that's what we're saying, it's going to shift right, okay? Okay, last one, adding a catalyst. Do what? Why would you say right? But are we adding or taking anything away from our reaction itself? No. So all that's going to happen is that we will reach equilibrium faster. But actually nothing at equilibrium is going to change one way or the other. A catalyst just helps us get to our destination equilibrium faster. But it doesn't take anything away from the reaction. It doesn't add anything to the reaction. It doesn't mess with temperature at all or pressure. So no change. Okay. So I tried to hit all facets of chapter 7. Okay. I would suggest you spend a good hour and a half to 2, depending on your comfort level with these problems tonight, going over these things. Don't just read your notes, like work problems. I really think rereading your notes is not a benefit in this class. I think working problems is the best thing you can do, okay? And if you get stuck on something, screenshot it, email me, and I'll look at it first thing in the morning. I have an office hour from 9 to 10 tomorrow. You can come in and ask questions. We're gonna go over gas laws, which is more math, okay? Sorry. And then Wednesday in lab time, we have a short lab to do. I think it's relatively short on hydrogen bonding, and we're gonna just spend the rest of the time reviewing chapter 8 and the gas laws, okay? So are there any questions from you guys on problems I didn't get to? The reaction diagrams? Yeah, that's right. I didn't do reaction diagrams, did I? Here, I'll do it on this because I'm recording this and people are going to want to see it. Oh, it's going to be 2 separate recordings. Dang it. Because it quit out in the middle. Whoops. Okay, reaction diagrams. So remember, this is your change in energy. Okay, your delta G. This is the reaction progress. So what are the different elements that we talked about on a reaction diagram? Like what information does it convey? How slow or fast the reaction is depending on what? How large or small the activation energy is. Okay, so let's just draw a diagram here. We always have the energy level of the what first? Reactant, so I always just put an R for reactant. We have some sort of peak. okay? So it means it goes up to some sort of peak. And then from here, the graph can look all kinds of ways. So maybe it finishes out right up here. And then what do we label at the end here? P for products. So now, how would you label your activation energy? Yeah, from what to the peak? Yep, from the start, which is right here, up to the peak, which is about, right there. We call this the activation energy. This is how much energy the reactants have to have for the reaction to go. They have to collide efficiently. They have to collide with proper orientation. They have to have the sufficient energy, which is the activation energy. Okay, and then we have a delta G too, right? How do we mark off or label our delta G? From the peak to the product? Right here? Is that right? It's not right. This is the difference between our reactants and products. This is the difference in energy between our reactants and products. So that's not a bad idea, but not quite right. So we would mark off our energy level of our reactants and our energy level of our products, and we'd find the difference between those things, okay? That's the delta G. Now, tell me this. Is this reaction endothermic or exothermic? Sorry, I meant endergonic or exergonic. Is this reaction going to be spontaneous or no? Why do you say that? The R is larger than P? Well, the energy level of the products is higher actually than the reactants, right? This right here is higher than that right there. You're not wrong, Jessica, but why is not quite right. Huh? It's not spontaneous, which means it's a positive delta G for this reaction. You see, we start lower and we just increase. An increase is a positive change in energy, right? A negative change would be like starting here and going down, and our delta G is lower at the products than it is, our energy level is lower at the products than for the reactants. But here our products are higher in energy. So this is an I keep getting endothermic, endergonic reaction, okay?
So if the reactant was higher than the product, then that would be
right. So let's draw another diagram. Here, I'll do it. Could y'all see it if I do it in purple? Is that a different enough color? So we have the same activation energy, but then our products were like way lower in energy, like down here. Okay. So if the products end up lower than the reactants, then we have oh shoot. I meant to go back to pen. Then we have here down to the energy level of our products, right? This is a negative delta G. So the red is an endergonic reaction. The purple is an exergonic reaction. Okay. So thanks for bringing this up. That was another topic from chapter 7 that was on there. It was a big one. Yeah, you'd say your products are more stable there because they're lower in energy. Zamara, I saw your hand first. So here the activation energy is the exact same on these, right? But if you have reactions that have different activation energies. So for example, let me just real quick. I gave you a bunch of different graphs. And it had one like this. Maybe it has one like this. Or maybe it has one like, I don't know. I'm just drawing a bunch of different stuff. Okay. You look at the size of the peak from the starting point of the line up. I mean, this one has the largest hill to climb, right? This one is the smallest hill to climb, and that's like a medium hill to climb. So which one would be the fastest? Which hill could you get up the easiest? Okay. This is the fastest one. It's the smallest activation energy. Largest activation energy. And this would be kind of in the middle. Okay. Good question. Did you have a question? That was your answer? Okay. All right, well, it's officially 3:04, so if there are any other questions?